Last session, heterogeneous memory systems, and Toni Peña. I mean, as I told you in the morning, there is alarm. Let's ignore it. And that's it. So, as I told you in the morning, this session of memory course started with introduction to heterogeneous memory systems that you guys actually started in 2017. At least this is the, you don't know.
You know more than me, yeah.
No,
This
is what I found, right? So then you had 9 iterations of this, and then you wanted to switch a bit. We wanted to make it slightly different, and this is why we are here today. Okay. So the difference of this slot is that it's not about tools. I think it's not a lot about tools.
No,
okay?
Yeah.
You will come to that. It's about context.
Mm-hmm.
And then we will come what it is, why do we have it, what are the problems, and then
how to deal with
them. How to deal with that, and here the tools come, right? So Toni, you have all the time in the world.
Sure.
I mean, until 5. and that's it. Have fun. Until 5. Yeah, you have time. You have time. Panel will be short. We'll do a questionnaire. Chill. Enjoy.
Okay, I prepared this for 30 minutes, but yeah, I can perhaps just speak a little bit slower than usual, which I appreciate. Thank you. All right. So yeah, just as Peter said, I will try to make it high level with touching just a little bit on the internals, but just a very little tiny. So if you're interested, we can discuss further on details. So this is the kind of the last session of today, and I'm sure you've got a lot of information. So let's make this a little more high-level conceptual. So I'll be talking about the concept of heterogeneous memory systems, why we need them, some examples of systems that we had in the past, some of the systems that I tended to say they are coming or emerging, but these days I'm becoming more skeptical. Let's see. What tools or what ways of dealing with them we have currently, but also what we have been doing, we and others have been doing in research to improve the usability. I drive a research group called Accelerators and Communications for High Performance Computing, in which a big focus of us is to enable high programming productivity, how to make users, HPC users or developers, dealing with the difficulty of systems, HPC systems, a little bit easier. High programming productivity is what we call it. So yeah, heterogeneous memory systems. As you may figure out, it's a broad concept covering whenever we have more than one memory subsystem within a given compute node. And that is very broad. These days, we have computers with scratch pads in some Japanese designs. GPUs have their own memory, and with unified memory, you can access more or less seamlessly the host memory and the GPU memory from the CPU or from the GPU. We have a high bandwidth memory. We started with, rest in peace, Intel KNL, also with Shaffer Rapids processors. Some of them were able to host DRAM plus high bandwidth memory. We have the machine from HP, was a big thing, but also finally this was discontinued. I was in love of Intel Optane persistent memory. Unfortunately, it was also discontinued. We expect more, and actually we have more already. With CXL, memory expansion, CXL memory pools, but as well, even if I've mentioned a few that are deprecated, there are some others that are still here. So what happens when we have more than one memory subsystem? And first of that, why we would like that? Well, some of them are obvious, like, for example, GPUs. Like when you have accelerators, they have their own memory, and it's obvious that you want one memory that is closer to the GPU, and memory that is closer to the CPU. You also have other designs in which the memory is shared, of course, but there's many, many designs. That's why we're here. So the main motivation is that the different memory technologies provide different features. And you may want to explode, if not all of them, of course, this is just a conceptual view, a few of them for different purposes. The most relevant one, I think, the one that is picking up most is whenever you want a large memory pool, you want to execute applications that require a lot of memory. Maybe you wouldn't benefit from distributing them across nodes to have more memory because just the network overhead, and also you may not need more processing power, you just need more memory. So then you want fat nodes, but you cannot just equip infinite amount of DRAM because of physical, thermal, everything, right? So then the memory technologies that provide larger spaces are slower, or at least that's the trend. Peter knows more about why. But what we see is that if you want faster memories, then they are smaller. Then you want bigger memories, then they are slower. So at least having some kind of DDR or HBM plus some NVRAM-like I/O class, like the obtained persistent memory that I mentioned, is a good combination. You can also have the DDR plus HBM, that's a Fire Rapids had. So anyway, there's low power memory, ECC-enabled memory, so they all bring different features that you may want to leverage, if not for your general purpose processor, maybe for something domain specific. So just a disclaimer from my side, because I will review papers. So I've reviewed papers in which they keep calling deep memory, but deep to me means kind of a relationship of hierarchy in all these traditional systems in which you access the L1. If it fails, you go to the L2. If it fails, go down and down. So to me, I will refer to heterogeneous memory when we do not follow this depth in which they are all brought as first-class citizens, right? Being whatever methodology, and we will talk about methodologies to distribute the data. But so for example, I name a few here. You can access them at page level granularity. You leverage the operating system's view. Just the operating system can monitor hot or cold pages, those that are accessed more or less, and then they can do migration, swapping in between different memory tiers, so that the ones that are accessed more frequently become promoted to the closer, to the fastest and smaller memory subsystem, and the others are demoted. But the operating system is the one that has that view. You don't see that. We will see that. Or if you have them exposed to the software, you can also decide where to place your memory objects. For example, when you do a malloc, I want to place it because I know this sub-memory, this data will be very critical. I'll be accessing it much than others and need it in the critical path, so it will be placed in the faster memory system. So I do a malloc here, or I do a malloc in the slower memory subsystem because I have a very big object that doesn't fit in this other one. You know, we can figure out manually or assisted by software those strategies. There could also be combinations, and there are other ways of doing this. So, a couple examples here. In the Fire Rapids with HBM plus DRAM. You have the processors, you have the HBM, and you have the DRAM, right? You have just regular DRAM, high bandwidth memory, which has a little bit more latency than DRAM, but I may be wrong. I've read a paper from you, and I may be wrong. But anyway, that's what I was always told. Anyway, you have, of course, this will be higher bandwidth than this, at least by the name, right? So the default allocation comes to the DRAM. You have to do something special that I will talk later if you want to go to the special HBM. While in Optane is this big memory that I mentioned that is non-volatile, but we use it like for as a RAM. So you can you have this biggest memory, but you have the DRAM, which is the smallest, as the default, and then you have to do special if you want to go to the Optane. CXL, I mentioned it briefly. Have you covered CXL across the? So I will also describe a little bit about it because I'm more interested in what it provides than what it is. CXL, Compute Express Link. This is kind of the future, present, or future that never comes. Let's see. So the CXL by itself is an interconnection specification across devices, being CPUs with GPUs, whatever, but it also supports attaching memory through this link. So with that, you can attach local memory expansion, which in the end, usually they are just DIMMs, DRAM DIMMs connected through a memory expansor that you connect to a PCI Express these days, and through the CXL protocol, the processor understands that there is more memory here, as in this case. But you can also do it on disaggregation. Memory disaggregation means that through the network, CXL, you can get this, it's kind of a separate rack of a pool of memory where you can share it with the other compute nodes whenever they need more memory than what they have available locally. So this is kind of already a reality which you won't find in production systems, but you can, if you are lucky, you can buy. I wasn't lucky, but Peter was. You know, in my procurement, they said they cannot provide it anymore.
I mean, we didn't buy it. We got it for free.
Ah, I need to learn how to do that. Well, I'll get the rest of the system, so maybe I can get free.
Yeah, we can make a deal.
I can pay under. Oh, this is being recorded. No. Okay. Anyway, this I have not seen even more than just people speaking about it and doing a lot of research, but I haven't seen materialized in something that I can actually access. But anyway, this has been a trend for a long time. I was hoping it would come like 2 or 3 years ago, or maybe next year. It's there. Let's hope. Okay, so. Yeah, I'm back to the deep memory. So you have this physically, right? They are distributed. But then you can lay out, at least logically, this way so that the hardware does it like whenever you are accessing caches, you know how the caching system works. So you fail in one level, then automatically it triggers the pullback from the other level. So you can lay it out in this way. So the hardware does it for you, like in an inclusive caching system. Both of them, okay? Then the downside here, well, there are several. There's goods and bads. Goods is totally transparent, hardware deals with that. Bads is you only see this memory space because this is an inclusive cache. You only see this memory space because this is an inclusive cache. You are also bound to the whatever approach the hardware has to migrate data. But I'm not against it. It's just this is easier, and I will show actually an example that we have that it worked great for us. But since the other approach, the heterogeneous memory mode, is more challenging for research, we have been spending more time on this. So in some cases, you see this as flat mode, updirect mode. The terminology changes, but anyway, the concept is that you have all of the memory subsystems available to you, to the software, being operating system, being yourself as an application, being some middleware, but at least from the software, you can see different memory spaces. So one immediate benefit is that you see more memory available. You can either, whoever software agent can decide to place memory here or here. But yeah, on the downside, you need some smart enough software agent to deal with that. Someone has to deal with it. And you are using CPU cycles to decide. In the other case, it was the hardware managing that. So how to use this? By the way, any questions so far? I'm going fast, even if, because I was ready for do it in half an hour. Any questions so far? Okay. Okay, so how to use this cool thing of having more than one memory subsystem? On the one hand, the first one, when you use the memory, just you configure the BIOS and it just does the magic. You don't see anything happening. You may see performance issues, benefits, downsides, but that's the case. But when you have more than one memory space available, all the systems I've been working with so far, by default, when you do a malloc or whatever allocation call, it goes to the DRAM. If you want to go to the other one, you have to do something. And that's something maybe just the operating system takes care, but you have to have an operating system that takes care of it. So if you want to use this without changing an application, for one way is with kernel support. So you can see the different memory subsystems, the ones that are not default, so as CPU-less NUMA nodes. So you see a NUMA node which only has memory but has no CPUs. Then That's your additional memory subsystem. And you can use NUMA-CTL to control where your memory will be placed by default. This is very coarse because you can do membinds, you can do preferred, so first come, first served. It starts going to the memory node, the memory allocations start going to that memory node until it's full, and then they go to the next one. You can control a little bit, and I will show an example next. You can do also automatic page movement or tiering. Since the Linux kernel 5.5, it's not default. It should be compiled and enabled by the system administrator. The concept is very similar to disk swapping. Whenever you require to access data which is not in the fastest memory tier, it will swap the page with another one. Okay, it's the operating system that does. All of this works even if the two or the different memory subsystems are exposed to the software, but without changing your application, right? You don't have to care from the application which memory subsystem your allocators target. So it has pros and cons. So these I've seen different memories exposed as NUMA nodes, and the kernel tiering apparently is becoming a default as a trend across the years. So an example of how the NUMA thingy would work. So you have the concept of distances across NUMA nodes. And this is a Sapphire Rapids processor with DRAM plus HBM. So you see that the DRAMs are tied in the same NUMA node as the CPUs. You have two sockets, and these are different NUMA nodes with CPU and CPU-less, with the HBMs. In this case, the HBMs are configured in a separate NUMA node. So by default, your application, if you change nothing, will start allocating in the memory in which the distance is closer until the memory is exhausted. So the first thing, it will start using the DRAM, not the HBM. Then the seconds will start using the DRAMs attached to the other CPUs instead of its own HBM. Then it will go to the HBMs, first own, next the others, and then it will jump to the other socket if we exhaust all the memory here and there is availability there. Okay, so this is the algorithm which is kind of naive and probably very suboptimal. That will happen unless you do anything, but it will just work out of the box. Things is when you start caring about having a little bit more performance, if that's part of your job, or you are performance geeks like myself or us in general in the BSC, right? We like high performance computing. We like scratching out the most last cycle of the processor, right? So a way you have to deal yourself, either from an application or from a middleware, decide where to place your data, is with APIs. It used to be Memkind, and a while ago it was superseded by UMF. There's the Unified Memory Framework from the One API, whatever framework or whatever it's called from Intel. Okay. So with this, it gives you APIs so that you decide your memory allocations where to go. So you have you can construct allocators and memory pools, and you also have some abstractions, utilities for memory management. So just to give you two APIs, I won't get into more details. The important thing is that you know the concept, that you have APIs or how to use when you have different memories. So first, you need to create a memory provider, which basically will target a NUMA node that you can specify with these parameters. And the allocations are internally made by mmap. But you have like this. You create a provider. And then you allocate a replacement for malloc, this is this call, in the specific provider. So de facto what you're doing is allocating in this or another NUMA node without letting the operating system do it for you. You decide. That helps if you really know where the memory that you are allocated, you want it to be. But also you need some kind of view of what memories you have in the system. So kind of a little bit, I would call it ninja programming. Right? You are coding specifically for one architecture and one application, but that may be what you need. What we have done is to research around this to try to provide something a little bit automated so that users don't need to care about this, and at the same time we get better performance than those other default mechanisms that I have shown, like the memory from the hardware, automatic tiering by the kernel, or this naive NUMA allocation by distances. So, as you saw, NUMA CTL sounds like a little bit coarse-grained. Everything is first come, first served. Whenever it's full, it just goes to whatever else happens to be in the shortest distance that has some availability. You have this UFM allocator, and there are others, but this is kind of the most prominent one. You specify the memory per allocation, but you may have also statically allocated objects, the stack that you cannot control. They will go to the default. It seems that shouldn't be a problem. It's just minor things, but we have found that those are the bottleneck in some cases. You have the kernel page movement. It's reactive because it cannot anticipate, or well, there are ways. There's research, but by default, the default is that it starts counting, and whenever this page is statistically more accessed than the other, let's migrate it. So it's a little bit reactive. By the time it does the migration, you may not need it anymore. So it doesn't have all the context information, which means, I mean, all of them have pros and cons. I'm not criticizing anyone in particular. I'm just going one by one. And it goes page granularity, which sometimes you have multiple things in a page. You don't really want them to all to be treated the same way. You can also control that from OpenMP or from MPI and from others, from SQL, one API, DPC++. For example, for OpenMP is pragma MP allocate, and from MPI you have this info key MPI memory alloc kinds. So it basically in the end will come down to those middleware using something like this anyway, right? But it does it for you in a more friendly way. Questions so far? How am I doing? Okay. So, as I said, in my group, we work on trying to make things easier for developers using complex systems. And this is one of the things. I'm not an expert at all in memories. That's Peter, and I ask him a lot. My area is more in high-performance productivity, programming models, runtime systems, and that's why I got interested in this challenge of how to help users deal with memory heterogeneity. So a little bit of starting point. When you do profiling, just regular profiling, you profile some code. Usually you get some statistics, perhaps per line, right? This is a code-oriented profiler. But we can also do the data-oriented profiling, in which we get our profiling metrics, whatever they are, attached to the different variables, data that we have here. So, for example, we could interpret this as we're spending 5% of our time here, 20% here, 75% here, or that, but this may not tell us much, depending on what we're looking for, or maybe we can see, 70% of the time we're spending on accessing this variable D, which is our vector, whatever, matrix. Okay, so we will leverage this concept. We implemented this concept of attaching cost to the different memory objects so that afterwards, first we can tell users, hey, this is the data that you should place here and there, or even do that ourselves automatically. So just a couple examples without entering in all the detail of how you can do this starting from the profiling side. So you can do instrumentation and cache simulation. With this, our target is to find all the last level cache misses. Because when you miss in the last level, you go to the main memory. When the main memory is not anymore just one thing, that can be several, at least two, hybrid, it will not, this last level cache miss will not take the same cost if it's served from a fast or from a slow memory tier. Right? That's why the idea is that we want to group the last level cache misses for all the different memory objects that we have. And those which have a greater density, meaning more cache misses per area, we will favor them to be placed in the smallest but faster memory systems. Okay. So this is what so we could do instrumentation and some cache simulation. We could also do sampling of hardware counters, which is the one that we have been using for a longer time. So you start sampling, because the hardware counters, and by the way, here's the worldwide expert, my colleague Harald. We start sampling the hardware counters because that cannot be as precise as this. We cannot just gather all of the last level cache misses, but we can ask from time to time how many have happened. And actually there is a way, which is called PEPs counters in Intel, SP in ARM, statistical profiling extensions, that you can even tie together the events. We link them to the original source code. So with that technique, Harald invented a way to, that's true story, to figure out how many cache misses we would have per memory allocation. So there's pros and cons, and these are just two examples that we worked in our team about this. Instrumentation plus software simulator, it's detailed but suffers high overhead. The cache is not the black box that we will have in the real hardware, it's just something that someone implemented. Or sampling and hardware counters with the BSC tools extra, they have Harald included that feature, that functionality. So the disadvantage that we're using the real cache behavior, it runs in the real target platform, it's low overhead, it's lossy by nature because it's sampling. We can configure the sampling period, but that's it. So in practice, both yield similar placements. You have some losses, but this one has the advantage that it's much faster. So in practice, we just used sampling and hardware counters, and it's much simpler. There are many, right? I put here a list of, it's non-extensive list of different solutions that could give you this kind of information of how many last level cache misses you may have for different memory objects, which in the end, the access pattern that you have to your main memory systems beyond the caches. So these give data access information to developers, but then here you have it, figure it out. Then you would have to go your code, and that's totally fine, but at least it gives you understanding so that you can target the mallocs here or there for your code. But we also researched in ways to make this a little bit more easier in case users would like to take it. So we developed something that in globally is called coexist, ecosystem for managing heterogeneous memory systems or something like that. One of the components is the heterogeneous memory advisor. Basically what it does is it takes the profile extracted by Xtry on how the different memory objects are accessing the memory outside the caches. And it just, well, this is what the naive algorithm, we have others. Basically it just figures out what's the optimal way of distributing the data across a very specific, that you specify across your system with heterogeneous memories. Right? You specify which memories you have, what's the default access, the average access latency, the sizes, and then from that output of the initial profiling, you analyze it, and then this advisor, the output is an optimal distribution. So of course it has limitations. There is no memory migration, so reuse of the freed space if there's many mallocs and frees, and you get a problem. There's ways that we researched to figure it out. But anyway, everything that I've been presenting has pros and cons, heuristics, nothing is super precise. So anyway, we are basing ourselves in the most informed possible guess that we have, and it has advantages in the end in execution time, as I will show. So anyway, this is the output. It tells you, okay, in this scratchpad memory, you place these memory objects. In DRAM, you place nothing here for whatever reason. In your 3D stack memory, you place all this. But still, well, with this tool is already very helpful, right? You know, then you go to your code, and you start modifying your mallocs by whatever API you have to allocate data here and there. But also, our colleague. This slide is not because you're here. I've been teaching this for 7 years. I've been showing this slide for 7 years. Well, so yeah, we developed, Harald developed with us a runtime component. So the idea is that during runtime, you intercept allocation calls, and then you inspect this output from the advisor. Oh, if you recognize it, oh yeah, this one has to be placed here. Oh, this one has to be placed there. Right? So it's fully automated. And it works pretty well just in our workflow here, which is called the coexist. So you have your original source code, no need for modification anytime. You compile it regularly and you have your binary. You execute it with just the preliminary call of line analysis. We call it that way, I think. So the memory profiler, based on extrae, does the magic, and it outputs a profile information. Basically, there are different metrics, but the one that we've been using the most is just number of last level cache misses per memory object, per allocation site. Then you run offline the heterogeneous memory advisor, and it outputs an optimized distribution specifically for your system. Then you go to the binary, you start the production runs. You just profile once, run many times. With the production runs, you attach the runtime allocator with LD preload, and every time it finds an allocation call, it will come here to this flexmalloc. Then flexmalloc, based on this object distribution, will do the matching. Oh yeah, I recognize this memory object. It should go here or there. So this is the one that does the calls to these allocators that I showed before, so that you don't have to insert them and you don't have to modify the code. So some results, I won't bother you, I'll just go quick over them. I didn't have the time to modify this animation. I'll just go over them. So basically, what you will see is most of them is higher is better, except for this one, which is lower is better. We checked with different memory sizes. We checked our methodology against the memory mode, which is the hardware, deep memory. Page migration by the kernel, and ProfDP is a similar solution that we beat. Okay, so, forget about much of the information. Our framework performs better than others, right? By different percentages that I will not go in detail. We know why. One interesting thing is that with smart placement, you can reduce significantly the DRAM, which is much more expensive and energy consuming, and favor big memory pools based on non-volatile RAMs, which are much more cheaper per byte and also less energy hungry. So with 1/4 of the DRAM, we saw little performance drop, thanks to this smart placement. We checked with the kernel page migration that it had at that time, that was a while ago, a very large cost in metadata in terms of size that limited also the available size. For example, these are micro benchmarks, something more complex like LAMPS, a molecular dynamic simulator. We weren't able to get performance improvement. It was negligible, it was just marginal. We implemented a bandwidth aware algorithm, which we improved up to 20%, Lulesh from 7%, OpenFOAM from some overhead to speed up, some other seismic tool from the case department at BSC. We also got very good speed up. For example, only 6%, where's the 6% here in OpenFOAM? Why would I care? Because I've shown very different results, right? And that's what I like. We didn't find any case at all ever with non-negligible performance drop down, something that you would notice, like less than 1% or 2%, something like that. So our improvements range from 0 to 2x. In return for just a profiling run, then no source code modifications or recompilation. This is just a tool with potential to help, with no touching your memory, your original code. Also great potential results for the DRAM reduction. This is another system that was with Optane persistent memory. This is with the Intel Sapphire Rapids with HBM. And we also get over 10% speed up with just attaching our tool, doing one profiling run. So you have here the pointers. This is open source. We're happy to help, to collaborate, to discuss. And quickly, I wanted to highlight, because yeah, this I know last part sounds like a little bit selling, but this what the thing that I can tell here. Right? This is an active project that I'm showing now, in which we found to work great with just deep memory, hardware managed. We don't need to manage it ourselves. The initial idea was to manage it ourselves, to find what was the specific problem, to develop some methodology to address this challenging problem. But we found out, actually, surprisingly, pleasantly, that just the hardware managed deep memory worked great. And it's called homomorphic encryption. When you encrypt homomorphically something, you can operate on the encrypted data without the need for decryption. And my experts are also there. Priyam could tell about this and Tatagan better than me. Anyway, so you can do some operations. Anyway, the key message, you encrypt, specifically for deep learning. We are leveraging this for privacy-preserving machine learning. You encrypt your model or your data or both. You send them to the cloud, and no matter what it is, the cloud will operate over it without being able to get anything because they are operating on encrypted data. Then you retrieve the results and then you decrypt using your private key. Magic. No, magic because you have more than 100 time memory requirements. That's what we were looking into big memory pools. And also the compute time increases accordingly. Oh, here's the nice animation. After you increase time and size, but everything is encrypted in the cloud. You just decrypt it whenever you are in your trusted environment. So thanks to obtain persistent memory pools, we were able to run the largest, at that time, model. And in our paper, we demonstrated that there was a very efficient use of this hybrid memory system consistent on DRAM plus obtain persistent memory just in using the deep memory mode. I can't remember anymore the name of Intel for that. But we did nothing. We expected to have some fun on the software to handle this. There was no need to do any software. The key was that it used a very linear access pattern, and it used very well the prefetchers and the internal buffers and everything. So yeah, it was a very efficient use. I won't have time to go into details. So, questions so far before I conclude? Good. Okay, summary, heterogeneity, all around. We are talking about not only GPUs anymore, by far. We're talking about SmartNICs, processing in memory, you name it. There's heterogeneity all around, big, little, whatever. And it also comes to memories. And it is here for good reasons, mainly for efficiency. So again, we don't have any more only processing elements. We have memories and others, as I said, SmartNICs, even the switches can do things. There are some heterogeneous memory management APIs in production, as I've shown one of them. They don't do much on helping you where to decide placing your data, but there are some research efforts on automating or guiding this data distribution that you can use. Besides what you have already in automatic hardware and kernel memory movements, which is already working, works good for some cases, for others it's not that good. I want to take a chance to make some publicity in our workshop. We have submitted the 7th workshop on heterogeneous memory systems to Supercomputing 26. Last one was in SC 2025. So if you are around heterogeneity and memory, please consider submitting, and this may be a good chance for you to visit SC, which we all enjoy doing. Chicago this year. I love Chicago. I was living there. And yeah, last but not least, we are open to advice, master theses, final year projects, host mentorships, collaborations. This is us, and this is us. Yeah, that's it. Thank you.
Some quick questions for Toni.
Is there any effort in trying to recognize before runtime, before running the program, which might be
Yes.
like static analysis?
Indeed. Static analysis, there's a lot of AI now trying to recognize patterns out of the blue. There's efforts, yes, a lot of them. I haven't brought them, but yeah,
Successful?
to some extent. Nothing hyper successful that you could generalize yet for everything.
Thanks for the presentation. And I'm curious to know more about sharing. Is it shared memory? You mentioned CXL, etc., but you don't get it currently. So is that cache coherence shared memory, or how do you map? Can you define or disable sharing? Or
Do you want to take this question? You maybe know more. No.
Oh, it's your slot.
Well, yeah, for the pooling. Yeah, for the pooling, I haven't seen anything close to production yet, and I've seen many promises and papers discussing everything, including and not including coherency. Some claim that they can do coherency super great, some others that the latency would be too much, so better to provide some other mechanisms. So yeah, this is still open. Far from, I would say far from production. I would dare to say that because even the local one is not that much in broad state.
so all the numbers you presented are in a tightly coupled system, not disaggregated.
Yes.
Okay, thank you.
Yeah, disaggregated, I've seen people claiming to have some access to some experimental platforms, but nothing that you can find usually around. It's easier to get the local, right? More. I thought they were in production, but I'm not able to pay for them. I mean, I have the money. They don't sell it. Thanks.
Last one. Good. Okay. So thanks for a lot.
Thank you.
I need your mic.
Oh yes.
It's